Hi everyone. For our project, we did an optimization problem on Black Friday shopping inspired by the holidays. My name is Liz,
I'm Matt.
And I'm Olivia.
and this is our project. We created a wish list of 10 items that are on sale for just one night. These items are found at many different stores, and we may not have time to visit all of them. With the time constraint of 2 hours, we prioritize the items on our wish list using a preference rating. The scale goes from 1 to 5, 1 being less desired and 5 being highly desired. We need to maximize the sum of the preference rating of the items we can buy given the time constraint. Here you can see our rating for each item on our wish list, as well as the index for each item used in our code. Our objective function maximizes the sum of preference ratings of the items we are able to purchase. Item sub k is a binary variable in which 1 indicates that the item was bought, and therefore the rating is added to z. When item sub k is value 0, we did not purchase the item and its preference rating was not added to the objective function.
As we mentioned earlier, we have a limited amount of time to shop, 2 hours, which is 120 minutes. This time is further constrained by the amount of time it takes to travel from one location to another, as well as the time it takes to wait in the checkout lines at each store to purchase the items. In addition, some items on our list are only available at one store, while other items are sold at numerous stores. Here's a map to help illustrate the problem. The time in minutes it takes to travel between locations is shown among the dotted lines, and the wait times for each store's checkout line is displayed in red on the store window. The items on the wish list that each store contains is listed under each store. As you can see, Target has the most items to offer of any store. However, it contains the longest wait time, so our program may decide to travel to numerous stores with short wait times instead of going to one place. Some stores are in complexes while others are in standalone locations, such as Apple. Our program states that it doesn't take any time to travel between stores within the same complex. We use two other variables in the formulation of this problem. Each store is represented as a binary variable, where 1 represents the store being visited and 0 represents the store not being visited. Each path between locations is represented as a binary variable as well, where 1 represents the path from A to B being traveled and 0 represents the path not being traveled. If a store was visited, then the items at that store are purchased and accounted for in the objective function. Additionally, we incorporated a constraint in our code that checks that the summation of the commute times for each path, plus the summation for time waiting in line spent at each store visited, is less than or equal to the allotted time of 120 minutes.
So here we have the results of our optimization problem. As you can see, the optimal value here is 29, which means that we purchased items that sum to a total preference rating of 29. The next part of our output is the item vector. This vector is indexed according to the item numbers in our wish list so that it can be easily interpreted. Here, we have purchased all items except items number 3 and number 5. The next part of our output is the store vector. Similar to the item vector, this tells us exactly which stores we visited on our Black Friday shopping path. In this case, we visited the first store, which is our house, as well as the second, fourth, eighth, and ninth stores. Finally, this big matrix down here is the path matrix. This tells us the paths that we took on our journey to each of the stores that we visited. I'll take you through an example in order to explain this component. Here, we will take you through our journey visually. We started our house, which is indicated with a 1 in the first element of the store vector, as mentioned earlier. In the first row of our path matrix, we find a 1 in the 8th column, which draws a path from location 1 to location 8. So, upon leaving our house, we travel to 12 minutes to store 8, where we buy items 8 and 9, a KitchenAid and a Google Home. We wait just 8 minutes at Bed Bath & Beyond to buy this, and we get a 6-point boost in our optimization function. We check these items off the wish list and move forward. Next, we observe the 8th row of the path matrix, which tells us to go to store 2. So, we travel to the Apple store and purchase items 6 and 10. Now, inspecting row 2 of the path matrix, we see a path to store 4, Walmart. Here, we purchase a nice Christmas tree for the holidays. We don't have too much time left to shop, so let's keep moving. Now, we travel to Dick's Sporting Goods in order to buy hiking boots, a kayak, and running shoes. This is indicated in our path matrix by a 1 in the 4th row and 9th column, indicating that we traveled from store 4 to store 9. Once again, we check these items off of our list and check the time. We're almost out of time, so we must head home. With just 12 minutes of our allotted time remaining, we make the 10-minute trip home. This completes our path. It is indicated once again by a 1 in the 9th row and first column of the path matrix. We weren't able to purchase all the items on our wish list, but we sure made the most of our trip.